In 4.3, these derivative rules that we're going to talk about are really just a whole bunch of shortcuts that we can prove using the limit definition of the derivative, but I'm not going to make you do that here. I'm just going to kind of show you the shortcuts. And it's going to allow us to work with more complicated functions more efficiently, and even just some simpler functions more efficiently. And hopefully these become second nature to you, right? A lot of what we can do in calculus is really made possible by all of these rules and these shortcuts that you're going to see throughout 4.3. And the first one is the power rule, which actually we just previewed in 4.2, right? So you might remember from 4.2, if we have something like x to the n, x to whatever power. Well, the derivative of that is to take my exponent, stick it in front like a coefficient, and then lower the remaining power by 1. So bring the power down, lower the power by 1. We learned that a coefficient times a function. Well, since this is based on limits, it follows kind of the same thing as the limits. I can take the coefficient and kind of leave it on its own for a minute and just derive the function as normal. However, if that constant number is on its own as a constant, the derivative, of course, is 0, right? The slope of a constant graph, a horizontal line, is 0. And kind of based on those last two things, and based on the power rule, right, kind of our specific case of the power rule, a linear term that we have here, so just something like, say, 3x, for example, right? All I'm left with when I have that is just the constant itself. Finally, I had mentioned this kind of briefly during 4.2. When we take derivatives, we can just derive term by term. So the sum or difference of a series of functions, when I derive that sum or difference, I can just take my derivative one term at a time. So all of these are things that we've kind of already dealt with. So for example, with my function here, and if I want to find the derivative, I'm just going to go term by term. So constant times the derivative of the function, right? So coefficient. So leave the coefficient out front and apply my power rule for x cubed. And I can kind of just chain my terms together. So again, coefficient, lower the power, bring the power down front, lower the power by 1. My linear terms just leave me with the coefficient, and the derivative of a constant is 0. So when I simplify this, I get 12x cubed plus 15x squared plus 2. And we can do the same thing with terms that don't look like powers because we know how to rewrite these as powers. So g of x is really just x to the negative 2 plus x to the 1/2. Now I have exponents, so now I can apply my power rule. Bring the power down, lower the power by 1. Bring the power down, lower the power by 1. To me, this is acceptable. In answer keys, you may see that they choose to rewrite it in fractions and radicals because that's the way that you were given it to start with. I prefer, as I've said before, I prefer in calculus to stick with just exponents. So that's just me. That was review. Let's try something new. We've talked about now the sum and the difference of a set of functions. Let's talk about the product of functions. So u and v are functions. And in order to derive this, here's what we're going to do. I'm not going to explain where this comes from for now because it just comes from the limit definition. I'm just going to show you how it works. Basically, everybody gets a turn to be derived. So I'm going to take u prime times v, and then I'm going to take u times v prime. And I'm going to add them together. So everybody gets a turn to have their derivative taken. U prime v, u v prime. Or sometimes you hear u prime v and v prime u. It helps to do a lot of side work here, right? It helps to do a lot of side work here and kind of get all your preparation figured out first. So here is my function. I have the product of two smaller functions, and maybe I can already define them as u and v, right? So here is my u, and here is my v. Whoops, that's not the highlighter. Here is my v. And off on the side, I like to, like I said, I like to kind of prepare my pieces first. So x squared plus 2x. Well, I need to find u prime as well, and so the derivative of that is just 2x plus 2, right, using the power rule. And then, again, 2x cubed minus 5. V prime is just 6x squared, again, using the power rule. And now all the pieces that I need are right in front of me. So I know the derivative. I'm just going to kind of copy and paste this so I can save some time instead of switching colors every time. Plug in as appropriate, right? So I know I need u prime, which is 2x plus 2, and then v, which is 2x cubed minus 5, plus u, which is x squared plus 2x, times v, v prime, sorry, which is 6x squared. And then I can go through and simplify if I really wanted to. I'll try to do this quick just for the sake of time. Minus 10x plus 4x cubed minus 10. And then I'm going to get 6x to the 4th plus 12x cubed. And I'm just going to combine my like terms. So I'm going to get 10x to the 4th plus 16x cubed minus 10x minus 10. And that's kind of my simplified combined form there. Let's take a look at a second example too. So again, I've got my u and I've got my v. I'm not sure why we picked u and v, but this seems to be conventional, which is a shame because u and v look so similar sometimes that sometimes it can be misleading depending on your handwriting or your font. So again, I'm doing my side work here, right? Set up u, find the derivative, 12x squared. Set up v, find the derivative, which is just 2, u prime, sorry, v prime. And again, I'm just going to term by term and just plug in what I need. The whole reason I want to do this side work is so that I've already got all of the tools that I need right in front of me, no questions asked, super easy to find. Not a problem at all. So u, v prime, and I'm going to try to simplify just a little bit. So I'm going to have 24x cubed plus 84x squared, 8x cubed minus 2, so I'm left with 32x cubed plus 84x squared minus 2. Product rule. Everybody gets a turn to have their derivative taken, u prime v plus u v prime, or v prime u, depending on how you like to write it.